Okay. Okay, so our next speaker for the morning is Vince Lazinski from University of Maryland. He's going to talk about vertex nomination, consistent estimation, and adversarial modification.
So thank you so much, and thank you for the invitation to speak at this workshop. I've been attending a number of the talks, and they've been wonderful. So we're going to talk. I'm going to talk today about some of the work we've done in this area that we call vertex nomination. Now, we invented that term, or not? I didn't. It was invented by a colleague of mine. But it's a general stand-in for sort of semi-supervised, lightweight information retrieval on networks. Okay. So this is based on work in two recent papers of ours with colleagues across academia and at industry. Our colleagues, Chris White and Jonathan Larson, are at Microsoft Research, and some of their problem spaces sort of motivated our applications in this area. So this is the vertex nomination problem in a nutshell, and I wanted to present it very informally first and then get to the formals of it as I progress. So the idea is, if you're given a pair of graphs, you're given vertices that are interesting in the first graph. And interesting here could really mean anything. This is you can think of it as a user-specified query. You want to find corresponding vertices of interest in the second graph. And so this is an artist's rendition of what the problem is. Here, and for the talk, I'm just going to focus on a single vertex of interest just to make things a little bit clearer. But you can have multiple vertices of interest and vertices not of interest as well, and that we can handle that no problem. So this is the problem. This is our graph 1. This is graph 2. We see the vertex of interest in graph 1, and we want to find corresponding vertices of interest in graph 2. And we've been working on this problem for a very long time, and recently we've started thinking about adversarial attacks or adversarial modifications in vertex nomination. And so the way we picture an adversary, and this is actually well motivated by theory, is that an adversary is somehow a probabilistic mechanism that comes in and acts on the network. And when it acts on the network, the pink here is the area that's been, the part of the network that's been contaminated by the adversary. It acts on the network in such a way that when you run your algorithm, your query algorithm again, it no longer can find interesting vertices, or it can't find them as readily as it could initially. And so in addition to having an idea of what adversarial noise is in this setting, we also wanted to think about how to regularize. And so we're going to present like a graph analog of the trimmed mean estimator from robust statistics, where we trim anomalous pieces of the network. That's this shaded region here. And after the trimmings, there's still some adversarial noise, but hopefully not as much, and our algorithm can then work again. And it's wonderful that it works in our artist's conception, but it'd be nice to see this working in practice as well. And so we have some illustrative simulation where we actually have a way of doing this information retrieval on networks. It relies on spectrally embedding the networks, the pair of networks, using some a priori known seeded vertices or correspondences across the networks to align those spectral embeddings, clustering them using Gaussian mixture modeling and clustering based on Gaussian mixture modeling, and then ranking based on distance to vertices of interest. And this is a very simple scheme, and it's simple because we wanted to try to understand it from a theoretical perspective, but it's actually useful enough where it has proven itself useful in a number of complicated real data applications. So this shows the embedding of the two networks under a specific model. We have a distribution in our schemes consistency class. That's this picture where the thing that you're looking for and the thing that you have are very close to each other. After the adversarial contamination, the thing that you're looking for and the thing that the training data that you have are no longer close together. But the regularization, after we use the trimmed estimator, the information retrieval works again. And so the story that we're going to try to weave here is that we have the networks, and in a clean setting, it's easy to find algorithms that work. When you have contamination, things start falling apart, but we can use this idea of regularization to pull us back into an area, into the realm where things work. Okay, and in addition to sort of an illustrative simulation, we have this nice real data example, which is, if you've been to talks about networks, you've probably seen this data 1,000 times, but it has proven useful in this Vertex nomination task, where it's this high school pair of high school interaction networks. We have a much bigger, more complicated real data example at the end, where you have high school students who are saying that they're friends based on Facebook profiles and then based on a survey. And I'm not on Facebook, but I understand that saying you're friends on Facebook doesn't actually mean you're friends. And so the survey data and the Facebook data differ dramatically here. And we can think of the adversary here as there are 82 vertices that appear in both networks. We call those the core. Those are students that appear in both of the networks. And we can think of the adversary here as adding extra vertices into the second network. So adding in these extra vertices to give, I think here would be 52 extra vertices that don't have correspondences in the first network. And now the task would be to find the corresponding vertices under this noise. And so it's like a chord jump type model. And I'll show better pictures of this as we go, but this is the idea. These are the two networks. In the core setting, this is the vertex that we're looking for in the second graph, and you see we can find it. After the noise is added in, these both have 82. After the noise is added in, the retrieval doesn't work anymore. And once you regularize, it works. This is, again, it's like a graphical rendition. But I think this shows dramatically what's going on a little bit better. So here, it's an information retrieval metric, so we can use some notion of precision at K as our scoring metric. And considering each of the 82 vertices as the vertex of interest, the one we're looking for in the second network, we can ask how many of those have their corresponding correct vertex of interest in the second network ranked less than or equal to X, and we can view that as a function of X here. And you can see that this goldenrod colored line is when we have no junk, no contamination at all. And higher here is better, it's doing fairly well. The red line is the contaminated setting, and once you contaminate, you see a marked decrease in performance. But I'll talk about how we do the regularization in a little bit. As you regularize the contaminated network, you can see they're effectively not doing enough. And some choices of regularization, like this light blue one up here, achieve almost the exact same performance as in the core setting. And so we can recover the clean performance in the adversarial setting by using this idea of regularization. And so we like understanding this just from these illustrative examples, but what we're after a lot in our work recently on vertex nomination is to try to understand this problem from a statistical perspective. So trying to understand some of the theory behind why things are working and why things aren't. And when we started working on this problem, I started working on it maybe a few years, maybe 5 or so years ago, and I had colleagues working on it back in 2011. And the approach was develop some algorithms, show they work, maybe show certain algorithms perform well under certain model assumptions. But after a while, we said, okay, well, if we're going to put a nice rigorous statistical background on this, we should start with the notion of consistency. This is the first thing we could ask for from a statistical perspective. And this is the textbook I learned basic introductory statistics from, Bickel and Doxam. And there's a lovely quote in the book, and it says, the least we can ask of our estimates is that as n goes to infinity, we have consistency. We have the estimates converge in probability to the thing we're estimating, the function of the unknown parameter. And this is sort of the first thing you could ask for out of an estimate. And if your estimate isn't consistent, well, maybe choose a different estimate, or at least in this asymptotic perspective. Okay. So when we initially studied the vertex nomination problem, it wasn't this multi-network setting. It was this much simpler setting here. And the original problem statement that dates back to this 2011 paper where the motivation here was looking for fraudulent activity or fraudulent actors in the Enron email corpus. The problem was if you're given a community of interest, that's this red community here. And in the original problem, these were the fraudsters. But whatever makes the community interesting is up to the user. And some vertices that these known red ones and are not, these known orange ones, part of that community, rank the remaining vertices into a nomination list with those in the community of interest, ideally concentrating at the top of the list. So the black vertices here, we don't know if they're interesting or not. And so we want to rank all of the vertices in the network into a list with the unknown interesting vertices concentrating at the top of the list. Okay. We formalize, in this problem setup, sort of the classical VN, as I call it, we formalized the notion of consistency in this Annals of Applied Stat paper from 2015. And we derived an analog of Bayes optimality in this Vertex nomination framework under a very restricted network model, under a stochastic block model. It's a fairly, if you're talking about communities as delineating interesting versus not, this is a natural choice for your first model to try, because it's sort of the base model that adds community structure to networks. And we proved that a spectral embedding-based VN rule is consistent under mild assumptions, very similar to the spectral embedding-based rule I talked about initially. In a sequence of subsequent papers, we proved a bunch of other VN rules were consistent and provided sort of more general procedures for implementing these things, paying attention to scalability and different aspects of the community structure that we could impacting performance. But all of the initial work that we did relied on the presence of having strong community structure among the vertices of interest in the graph. And sometimes that's reasonable. And it's this community structure that defined interesting, and sometimes that's reasonable. But I started working some with some NLP colleagues, and we had these vertex nomination algorithms, and we thought, okay, they're hammers. Let's try to apply them every time we see a nail. And so I had colleagues who said, okay, well, if we can do these unstructured queries in networks, then let's try to do these in knowledge bases. And so they are knowledge graphs. And so our initial test of this is we chose some vertices in the knowledge graph that had interest that we thought would be interesting, and went to see if our algorithms could perform well, and our algorithms all fell flat on their faces because it wasn't community structure that defined interest in there. It was some other combination of features that we were not leveraging at all. And so the particular features that define a vertex are interesting are entirely subjective. And actually, often part of the challenge in this problem space is that if you want this to be these general approach to information retrieval on networks, you want to be able to, in some sense, learn what made vertices in the query interesting in order to go search the second network for similarly interesting vertices. And for an example, we had vertices with a large network centrality might be the ones that are interesting. Vertices that play a particular role in a network, corresponding to a given user across social networks. And this third example, and the NLP example I mentioned earlier, motivated the newer formulation of vertex nomination. That third example, we, working with some colleagues, we had Twitter data and Instagram data that we scraped. This was back when that was easier to do. And we had a friend who was both on Twitter and Instagram, but his username was different across the two networks. And we thought, well, a fun challenge would be to see if we can identify him using our VN algorithms. And in this, it wasn't the community that our friend belonged to that was interesting, but it was the friends that he had that made him interesting. And so we were able to actually do fairly well in identifying our friend. And it made us push this problem space further than we had before. And this is the new formulation, then. I call this the V2 statement of the problem. So given a vertex of interest in a graph, find the corresponding vertex of interest. And again, I'm talking about a single one because it's easier to talk about. You can have lots of vertices of interest, that's no problem. Ranking the vertices into this nomination list so that the interesting things appear at the top of your list. Okay. And in order to move past the idea that communities delineated interestingness, we situated this new problem framework in a very general class of distributions that we called nominatable distributions. I'll give a full caveat. We are awful at naming things. And so our acronyms are always unpronounceable. And the names we give things are, they're very straightforward, but seldom elegant. So nominatable distributions are distributions we can nominate from. And I won't give the formal definition because it's very notation heavy, but I will say that this collection of distributions encompasses many popular network models, from the independent edge models that are that we had been working in previously, or even conditionally independent edge models like dot product graphs or latent position graphs, to more dependent models like preferential attachment, Watt-Sturgot's, exponential random graph models, and so on. So it encompasses many of these popular network models. We tried to make it as general as possible, and it allowed for a very general definition of what made things interesting, what corresponding interesting vertices meant. Okay. And the first question we said, well, great, we generalized the problem, and now let's ask about consistency in this new setting. And so our motivation for this was, we went back to the idea of consistency in the world of classification. So this is just a step backward in time to the DeVroy, Gyorfi, Lugosi book that I learned that has a really nice treatment of probabilistic classification. So remember classical consistency in a classification setting where you have NIID or training data points. These are the data, these are the labels, and then the task is given a new X, label it, find the unknown label Y, and these are all IID points. That's your training data. And a classifier is just a function that takes the training data and the unlabeled X and spits out a label. I'll deal with binary classification because that's enough for now. And the error of your classifier under 0-1 loss is just the probability that your classifier is wrong given the training data. Okay. The Bayes error is the optimum. This is the gold standard, the best you can do, and it's just the infimum over all classifiers of the probability of being wrong. And in the 0-1 class case, it's easy to derive the Bayes error. And you can then talk about, once you have Bayes optimality, you can talk about notions of consistency. So a classification rule or a sequence of classifiers is consistent with respect to a distribution F if the loss function in expectation converges to Bayes error. And it's strongly consistent if the loss function almost surely converges to Bayes error. And a rule that's strongly consistent for all distributions F is called strongly universally consistent. And strongly here's in parentheses because it can be just plain universally consistent as well. And universal consistency is a really important idea in classification because it effectively says that classifiers, given enough training data, a classifier can effectively accommodate any eccentricities that a distribution can throw at it, a universally consistent classifier. And for a long time, the existence of these things was unknown until Stone wrote the landmark 1977 paper showing the first example of a universally consistent classifier. Okay. So back to VN, that was my brief segue. What is a VN scheme and how do we talk about consistency in this new framework? Well, a VN scheme is nothing more than a ranking function. And there's a technical internal consistency property I'm not going to get into because it's not important to understand what's going on. But a VN scheme is nothing more than a function that takes the graph, the first graph, a version of the second graph that has its labels hidden so that there's no information in the labels in the second network, the vertex of interest, and then it spits out a rank list of the vertices in the second graph. So it takes the two graphs, something that's interesting, and spits out a rank list. And since the idea of this framework is efficient network data mining, it makes sense that, well, in a perfect world, the interesting vertices that you're looking for would fall immediately at the top of your rank list, but this is too much to ask for. So if the vertices of interest are near the top of your rank list, that's a huge win. And if there's tens of thousands of vertices in your network and you can find a few vertices in the top 10 of your rank list, that's a huge win in terms of network data mining. And so this motivates our loss function that we consider in Vn. The error of a vertex nomination scheme is the probability that the scheme ranks, so the level K error, is the probability that the scheme ranks the vertex of interest in the position K+1 or higher. So in fact, the level 1 error would correspond to the probability that the thing you're looking for in the second network is ranked 2 or lower, or 2 or higher, I guess, higher being 2, 3, 4, all the way down. And depending on the user's, the amount of the network they can actually check, different Ks are of different utilities for different tasks. But this is the way to sort of, in a precision at K type framework, provide a loss function here. Okay. And this allows us, once we have a formal loss function defined, it allows us to define the notion of Bayes error. Bayes error is just anything that minimizes the loss function, any scheme that minimizes the loss function. And it turns out in this, in the 2019 JMLR paper, we can derive a Bayes optimal Vn scheme. Note that it doesn't have this subindex. It turns out that there's one vertex nomination scheme that for a given distribution is Bayes optimal for all K simultaneously. And we were able to, the definition's a little bit complicated, but we were able to construct that scheme. And so now we have a gold standard to shoot at. We have a notion of Bayes error, and we have a Bayes optimal scheme, and we know that at least one Bayes optimal scheme exists, and it's Bayes optimal simultaneously across all levels of error. Okay, so this allows us to then define consistency. And if you have effectively consistency in loosely stated, just means that the loss of your, if you have a Vn rule or a sequence of vertex nomination schemes, that your loss converges to Bayes loss as n goes to infinity. N here is the size of the network. And so for a given non-decreasing integer sequence, a Vn rule is level Kn consistent. Note that K can depend on n, it need not. With respect to a sequence of distributions, if the limit as n goes to infinity of the difference between the Vn loss and Bayes loss goes to 0. Okay. And we define this idea of Bayes optimality. We can define an idea of consistency, and we thought, okay, now we're cooking. Now we can sort of go and try to show all these nice properties of vertex nomination schemes, and in the schemes that we've developed, we can try to show that these things actually work. But before we did that, we had some sort of odd findings, or I should say surprising findings, perhaps. So back in the classification setting, the idea of training is very well defined, right? You have these n training data points where you have label and data, the xi, yi pairs, and you leverage that information to label your unlabeled point. So the idea of training is a lot clearer. Vn doesn't really fall into the classification framework. The idea of training in this case is a little hazier. And in some sense, the training that you have is the network. You have this lightweight supervision, but also you observe both networks. And you can imagine that the training information now is the edge structure of the networks. We have lifted this to the case where you have features as well, and in which case the training would be the edge structure and the features. But it's the line between training and quote unquote testing here is a lot vaguer. And in some sense, the sizes of the two networks, n is the size of the first network and m is the size of the second network. These, rather than think of this as the training set size, think of this as measuring some notion of problem dimension. Because the idea of training here, it's a little bit hazier. And we have spent a fair amount of time trying to jam this into the classification framework, and we haven't been able to quite make sense of that yet. But this idea that the training is a little bit hazier has a very strange ramification. So classification's universal consistency relies on somehow the distribution not changing in n. And the training data eventually can overcome any model pathologies. And this is not the case in vertex nomination. Even if the distribution is really not changing in n, we have this theorem that says that there is no such thing as a universally consistent vertex nomination scheme. And the theorem is actually maybe even worse than that, because it says, give me an arbitrary epsilon and any Vn rule that you want. I can construct a sequence of networks for which the Bayes error for that sequence of networks converges to 0 or less than epsilon. And the error of the vertex nomination schemes that you gave me converges to 1. So the Bayes error is bounded above by epsilon, the lim sup of it's bounded above by epsilon, and the error of your Vn rule, the sequence of errors, is converging to 1. So not only are there no universally consistent schemes, but in the limit, I can construct a sequence for which you do arbitrarily badly. And that was a very surprising result. And we thought, okay, well, what can we do about that from a practical perspective? And our first thought was, well, what if there's not one Vn scheme that works for all distributions? But what if we can sort of have a small number, a finite number of Vn schemes that can be there? If you talk about the sets of distributions for which they're consistent for, they would tile the whole space. So this led us to the idea of consistency classes. So a consistency class in vertex nomination is a set of distributional sequences for which there is a rule that's jointly consistent for all of them. And if I add a single new distributional sequence to this class, there is no rule that's jointly consistent. So this is somehow a maximally large class of things that one rule works for. And our thought was, if we could divide the set of nominatable sequences into a finite number of these consistency classes, then we could get past this lack of universal consistency using an ensemble approach. And unfortunately, that's not possible. So if we could partition this letter is the set of all nominatable sequences, so sequences of nominatable distributions. Can we partition that into a finite number of consistency classes? And the answer is, unfortunately, no. Under mild assumptions, any partition must include infinitely many pieces, which means that in order to build an ensemble scheme that's universally consistent, you'd need an infinite number of elements in your ensemble. And so that was the first result that sort of thwarted our effort to overcome this. And there's an even worse it gets worse than that, in that without additional metadata or features, you can't even tell if a given distribution is in the consistency class for a given scheme. So if you think about vertex nomination sort of in the wild, running, we can develop an algorithm, we can pass it off to partners of ours, and they can implement it on their computers and then run it on their networks. And in an evolving network setting, they could run it on this evolving network. And if there were universally consistent schemes, then they would have at least a hope that their vertex nomination rule was working regardless of where the evolution took the network. The lack of universal consistency means that not only can the network evolve so that it's no longer in the consistency class of the scheme, but this fact means that they won't know that that happened without additional metadata or features. And so in some sense, there's an idea of, in this semi-supervised information retrieval framework, of the utility of a user in the loop. And in vertex nomination, looking back, many of our best use cases involved having a user in the loop who could provide lightweight supervision at various time points. So we would run our approach, they would maybe look at the top 10 things we gave them after a certain amount of time, And they would say, okay, yes, yes, no, no, yes, yes, we go feed that back into our approach and continue. And the utility of that, it turns out, wasn't an accident. That was, in some sense, a necessary piece in order to overcome this idea of the lack of universal consistency. And not only that, but we thought, well, this idea of not having universal consistent schemes can really be exploited by a model for adversarial activity in vertex nomination. Now, this is my artist's rendering of what the action of an adversary is. This letter is supposed to be that script N that we saw before, the set of nominatable sequences, but it's not quite as elegant looking. So this blue egg-shaped object is the consistency class for a given vertex nomination rule. And you can see we have a distribution in that class. And the red out here are rules for which our class is no longer consistent. The adversary can come in, and the action of the adversary can be thought of in two ways. It can either shrink the consistency class for a given rule. So this is now the new consistency class, and note it's smaller, and the distribution has been moved out of the class. We no longer work on that one. Or you can think of it as actually moving this distribution out of the consistency class. Either way, the adversary can be understood as taking distributions that were in the class, modifying them probabilistically so that they're no longer in the class, in the consistency class. Okay. And we can formulate this probabilistically as follows. So if we have a distribution on graphs, and the adversary is going to be acting on the second graph, so that's the N here is the size of the second graph. And this is the set of labeled graphs with M vertices. And we have some random variable independent of the graph that we're going to pull from this distribution F. An adversary then is this probabilistic mechanism that has 4 parts. It has, this is the parameterization of the adversary. It has a function F, which takes the graph, the independent source of randomness, and the set of parameters, and spits out a new GM valued random variable. It has this function V, which takes the graph, the independent source of randomness, and the parameter, and spits out a potentially random subset of the vertices of G. And these are going to be the vertices that get contaminated by the adversary. And then this, you can think of an important feature is this set, capital K, which is the set of vertices whose the edge between them in some sense was contaminated. So it was an edge that appears in the adversary or in the original graph, not in both. This is the symmetric difference function. This set of vertices that have their edges, that have adjacent edges that have been contaminated, all of these vertices have to fall into VA. So this actually does give us the set of vertices that are contaminated. Okay, and U here represents this independent source of randomness that we can utilize in the adversarial attack. So the adversary now can be understood as this probabilistic mechanism. You can think of it as adding or subtracting edges from the network, but that can also be thought of as adding or subtracting vertices from the network if you think of the piece that you didn't contaminate as being the core, and the edges, the vertices adjacent to edges that you did contaminate as being the periphery, then you could think of this as being a vertex adding adversary, a vertex deleting and adding adversary as well. Okay. And the idea is the adversary contaminates the model to move the distribution out of a scheme's consistency class. And we saw in the illustrative example from the beginning of the slides that we actually have examples of schemes and distributions for which the scheme works in the clean setting, the adversary moves you out of the consistency class, and regularization comes and brings you back in. And the example that we showed in the first batch of slides was a very simple example, and it's coming from a two-block stochastic block model. So imagine I have 2 stochastic block models that are coming from the same distribution. Each one has n/2 vertices, and they both have the same block probability matrix B. So with probability P vertices in block 1 have an edge between them. With probability Q, vertices in block 2 have an edge between them, and there's, with probability R, vertices across blocks have an edge between them, and all edges are independent. Here, we already condition on the block labels, so the independence of edges follows them, okay? I have this model, and the adversary that will we propose acts as follows. It picks some subset of the vertices randomly with probability pi plus, and then some subset of the remaining vertices randomly with probability pi minus. For each vertex in the class, in the W plus set, the edge addition class, and each additional vertex, if there's not an edge between them, add an edge in with some probability. For each vertex in the edge deletion class, if there's not an edge between them, if there is an edge between them, remove it with some probability, okay? And the interaction between the contaminated classes is unchanged. This takes this 2-block stochastic block model and lifts it into a 6-block stochastic block model, where these are, you can think of as the red number, the red here corresponds to pieces that weren't contaminated or that we didn't select to be contaminated by the adversarial noise. This is the edge addition class in block 1, edge subtraction, edge deletion class in block 1, edge addition class block 2, edge deletion class block 2. And it's a very simple model, and we like simple models because it allows us to perhaps try to understand them from a theoretical perspective. And we were really happy. We were like, this is a lovely model that we developed. And then we went and we found that there's this paper by Tony Kai and Xiaodong Li that proposed almost the same model. And so we thought, even better, someone really smart thought of this model before us, so it can't be that terrible. And under this model, we have this vertex nomination scheme where a spectral embedding on alignment of the 2 graphs in spectral space, and then a nomination, you cluster them using Gaussian mixture modeling, and then do a nomination based on Mahalanobis distance, given the Gaussian clusters. This thing actually works. We can show that this thing works under the clean model. The clean model is in the distributions consistency class. After you contaminate empirically, and I think we are able to show more rigorously, this after the contamination, that 6-block model is no longer in the consistency class with with certain contamination parameters. And after we do the trimming, which the regularization is this trimmed mean estimator, VM works again. And so let's talk about the regularization, because that's been the one thing that I've mentioned a bunch of times and haven't even talked about yet. How do we regularize? Well, the motivation for this problem was a graph mining task coming from colleagues of ours at Microsoft, where we have Bing entity transition networks. We have different ways that people can traverse these between entities in Bing. And we wanted to be able to figure out if we could look for similar groups of entities from one graph in another, in the other graph, with the way the edge structure is defined by the different ways people can traverse these networks. And our colleague at Microsoft, Jonathan Larson, had been for a long time working with a rule that we have dubbed Larsons Rule. And Larsons Rule was effectively trim the noise off the network using something like a trimmed mean estimator in network world. In classical robust statistics, the trimmed mean estimator takes the top some percent of the data, the bottom some percent of the data after you've ordered your data, trims those out, and then computes the mean. And this is a classic tool in robust statistical estimation. The trimmed graph, the trim mean analog in graph world, is you take your network, you order the vertices based on degree, you chop the bottom X% off and the top Y% off based on the degrees, and you leave what's left. How do you choose X and Y here? Well, Larson's rule gave us a way of doing that based on network modularity. So then if I'm given a set of communities in a network, I can define the modularity of as follows. So E is the number of edges here on our trimmed network. A is the adjacency matrix of our network. D is the set of degrees. And CI, again, this is given a set of communities. CI is the cluster containing vertex I in that community assignment. And so modularity gives a sense of, it gives a numeric score for how tightly connected communities are within versus across. And the higher the modularity, the more edges within community versus across community that you have in your network. And so the Larsons rule says, choose X and Y, do a grid search over X and Y's, trimming off various amounts at each time, and choose the X and Y that maximize network modularity under some clustering of the original network. Okay. And it turns out that this works remarkably well in practice. So this is an example in that simple stochastic block model example. This is the network modularity versus the X trimming and the Y trimming. And actually, this is the X trimming, this is the Y trimming, or vice versa. And this is the one of those figures showing the number achieving rank less than or equal to X versus X. So if we look at the core of these two networks, the pieces that haven't been contaminated, and you ask, can we find these vertices across networks? This shows the number of those vertices that we could find in the top X of the rank list. That's the Y here. Higher is better. That if we only look at the cores and have no contamination, it's this light green, it's the kind of odd yellow-green line up here. And you can see that if I choose the contamination to be L.1H, so L here is X, H here is Y, L.1H equals 0, then my contamination, the regularization I perform brings me back almost to the perfect, the setting where I have no contamination at all. And not only that, but that was the value predicted by our modularity estimator. So we have this way of doing this adaptive regularization that in both simulated and real data networks seems to pick sensible parameters for the regularization. Okay. And I have only a few minutes left, so I'm going to skip the friendship example. I'll only say that we do have the same phenomena holds here, where the adaptive regularization, the regularization it tells you to pick, actually is the one that gives us really good performance, or that is able to bring the performance in the contaminated setting back up to the clean setting. Okay, because I want to get to the last example, which is sort of the motivating example for all this work. This is Microsoft Bing entity graph transitions, where we have a multi-graph from 1 month of aggregate Bing entity graph transitions. Edges are the transition rates between two entities that users make while browsing. And the edge, there's two different graphs, or two different edge types. There's transitions that were made via a suggestion interface. So Microsoft will actually say, oh, you're at this node, you should search for this thing next. And there's transitions that were made in a free-form interface where there was no suggestions being added. And one of the ideas that they wanted to explore was, is the search structure similar enough where we can still find similar groups of entities in one network versus the other network, or is something going to be fundamentally different between the two graphs? Okay. In the first graph, there are in the core, so these are vertices that appear across both networks. There's like 13,500 vertices. In the second graph, once we add the vertices that don't appear in the first network, we have roughly 45,000 and change, and you can see these are the number of edges. So we do that same experiment where we consider each core vertex and we look for the analogous core vertex in G2 in the presence of contamination and after regularization, and when we're only considering core versus core. And we plot the number, again, achieving rank X versus X. And for now, let's just pay attention to this left figure. Again, that gold line shows how well we're doing in the core only case. Larger is better. The red line shows how well we're doing in the contaminated case. The blue and the green are regularizations that are overly draconian. They're regularizing way too much of the network. And the pink here is the regularization that was suggested via the modularity Larsons Rule. And you can see that although we're not able to recover the performance in the clean setting, we still have, this is only trimming 10% of the top and bottom of the networks. So we have 46,000 vertices, so it's only trimming roughly 9,000 total vertices. We still have, I don't know, 36,000 vertices versus 13,000. We're still able to recover a huge chunk of the missing performance. So the red down here, our performance falls off a cliff, and we're able with this regularization to recover a big piece of the missing performance. Okay. So we're pushing this idea further. This idea of trimmed mean estimation really makes a lot of sense if you have an adversary that's coming in and adding or removing edges, because then overabundant edges or too few edges marks a contaminated node, and those would be ideally the ones that get trimmed. We're working on developing adaptive regularizers that, if the adversary is acting more locally or acting in a different fashion, would be able to identify that and sort of cleave the network accordingly. And we're also going back into this idea of universally consistent schemes don't exist, but if we could perhaps say, if your graphs are well behaved enough, we can find schemes that would be consistent or close to consistent if your graphs are good, are nice enough. And so can we find sort of maximal families for which universally consistent schemes exist? And we suspect that there's a property analogous to the graph sample coming from a single common distribution. So you can think of these as being graphs coming from something like a graphon, where the vertices can be thought of in a streaming fashion with a common probabilistic mechanism for how they connect to the rest of the network. This we suspect this is essential, but it's not enough. We have examples in this setting where we still fail. And we've been working recently on exploring covariates in this setting. From a theory perspective, there's a give and take between the topology and we call it the context and the content of a network. So the connectivity and the covariates on vertices and edges. And we have a very recent paper where we explore from an information theoretic perspective when it's better to use both covariates and edges versus just one or the other, because it's not always the case that using the network's going to add anything, or using features are going to add anything, especially if those features are not what's delineating interesting or not. And we're working also on different formulations of this. I call them VN formulations, but they're more general. So you can think of, if this is just a general framework for lightweight information retrieval, then why are we just retrieving vertices? We could think of doing subgraph nomination. We could think of doing things like functional nomination for nominating collections of vertices that have the similar roles in the network, or things like that. So we're pushing this problem further, both from a theory and a practical perspective. And I did want to, these are some of the references from the talk. And this is the obligatory thank you for the monies.
Okay, thanks for the really interesting talk. If there are questions from the audience, please raise your hand or type the question into the chat box. Let me ask a question to get things started. With these adversarial attacks, I was wondering, are these sort of like what we call white box attacks or black box attacks, in the sense, does the adversary know the VN scheme that's being used? And is that part of the attack?
The answer is no. The actual scheme being used is not part of the adversary as we define it probabilistically. We could put that in there. We wanted a general framework, so you can think of the adversary as being this type of a global adversary that in our model, where it adds and subtracts edges, is just one example. But we have other examples where the way the adversary is contaminating the network is different. And in practice, you would imagine that the adversary would have knowledge of what the scheme was trying to do. And building that in, I think, would be something that we could do.
Right. I suppose you would get worse results somehow, or they would be easier for the adversary to corrupt in a bad way.
Yes, and there's this give and take between, so one form of regularization is this idea of actually going in and doing something to the network itself. Another form of regularization is this idea of supervision. And it's the user in the loop supervision you can think of as being somehow a regularizer, because it can, in that setting, you're not changing the graph, but you actually can change how the scheme is nominating. And so we have these kind of fun now back and forth between an adversary who messes with the network and a user in the loop who can say, okay, you need to change what you're doing. And then you can see the interplay between that.
Okay, nice. So there's a question from Nicholas. I'm going to unmute you, Nicholas. Oh, okay.
Hi, Vince. So I have a question. So okay, so of course, like when we talk about consistency, so it matters the model, I guess, but also kind of like your class of functions. Let's say like for the classification analogy. But here, so in other words, here my impression, or maybe I missed something, is that you're looking for arbitrary nomination functions, like arbitrary nomination schemes. So there is nothing constraining what these nomination schemes can be. So in a sense, like this is a very large kind of a space. So I mean, am I interpreting something incorrectly, or is this something that could provide perhaps a direction to how to recover consistency? If, for example, you say, the nomination schemes that you have to use have to satisfy some properties. If I imagine, I don't know, some sort of continuity, like, if you have nearby vertices, that they have to nominate things nearby in the other graph. Yeah, so I wanted to ask about that.
That's a great question, and I'll answer that in two parts. We wanted to keep it fairly general because we wanted to allow for different behaviors of the function. But this internal consistency property that I had I said modulo, a technical internal consistency property, is a fairly large constraint. And this is a constraint that essentially says your nomination schemes have to be sensible, in that they have to, in some sense, since we're doing this from a network topology perspective, they have to respect the topology of the network and not just the labels of the graph, because the labels, there's in some sense no information about them. And so it's actually a very strong constraint, and it really limits the set of nomination schemes. But we can also look at, as you said, subsets of the class of nomination schemes that have to have certain properties, and study Bayes optimality under these restricted classes. I don't know, in the original setting where we had block models as our working assumption, it was a little bit easier to do that. In this general setting, we haven't been able to make heads or tails of sort of a sensible way to restrict it to the point where we were still able to have enough generality to come up with a notion of Bayes optimality.
Right. So now, for example, if we take this analogy of like what you're trying to do here of matching vertices of two graphs, and we pose this problem as a geometry problem where we have like two manifolds or something like this, and then we wanted to ask a similar question. We wanted to say, how do we for every point on manifold 1, how do we associate manifold 2? So do you know if anyone, what would be an answer or a canonical answer to that question in the geometric setting? So as to, I don't know, I guess get a feeling of, similar things that you can impose on the graph, general graph setting.
Yeah, so that's a great question. We have, I want to, I'll say two things on that. So the idea of there being matched points, in my examples, that was the case, but we don't want that at all to be a restriction. So in some settings, we've applied this, and the NLP query that we actually motivated some of this work. We were trying to query this large knowledge graph. And the query that we actually used was we put a list of 10 female American authors. And we wanted the nomination scheme to then return a rank list of people in the knowledge graph with female American authors concentrating at the top. And it turned out that it didn't, because a bunch of the authors were also politicians, and it keyed in on that too much, and it returned a bunch of politicians. But there was nothing to make those things be matched. They were just, they were similar in feature space and in a subset of feature space. If I'm actually looking to match identical or similar vertices across networks, and I want a one-to-one correspondence, there's a huge amount of work in like network matching or graph matching, where you can get results on how much noise you can have in the second network in order to still guarantee a perfect recovery and across the two. And those often, I think most of those results are in very simple network models, and so not getting, and not these sort of manifold derived cases, but you could imagine similar ideas working in the manifold cases, perhaps. But what makes things interesting, we want it to be very general. And so it's not that interesting means you're the same person across networks necessarily, or the same entity. It could mean that interesting to me might be people who play a role in like a given organization. And I could be looking for more people that play that role in the larger network. And so those things might be very far apart in manifold space, because depending on how you define the manifold, right? And so what features are being keyed in on here to define quote unquote interesting is vague and purposefully so.
Thank you.
Yeah, you're getting at one of the key things, though, because the problem is so general that if universal consistency existed, it would also have been greatly surprising.
Okay, great. So thanks for the great talk. Let's continue the discussion in the breakout rooms.